Hello, class. In Chapter 2, we're going to cover motion in one dimension. Another word often used to describe motion is kinematics. Before we dive into Chapter 2, I would like to go over a definition from Chapter 3, and that is vector and scalar. A vector has magnitude and direction, whereas a scalar only has magnitude. Think of magnitude as an amount of something. Some examples of vectors is displacement, velocity, and acceleration, because all of these variables have an amount represented by a number and a particular direction. We represent vectors by drawing arrows. The arrowhead represents the direction and the length of the arrow represents the magnitude. The picture on the right shows the arrowhead and length varying as the car makes a turn. Now some examples of scalars is distance, mass, time, and temperature. All these variables have an amount, but no direction associated with it. Knowing the definition of vectors becomes more important in later chapters. Now on to Chapter 2. The first concept you're going to learn is the difference between distance and displacement. Distance is the actual path traveled by an object as represented on the graph by the dashed line. And displacement is the measurement between the starting and the end point. In this particular case, the actual path traveled is 70 meters, but the displacement is only 40 meters. Another way to think about the difference between displacement and distance is to imagine that you are hiking through the woods on a winding path. The distance is represented by the actual trail that you hiked on, and the displacement is a measurement between the start and the end of your hike. Take note that you actually never traveled along the displacement. To understand the equation that represents displacement, we first must know that the variable x in this course will represent the position along the x-axis. The Greek variable delta that you see as a triangle is used in this course to represent the change in variable. Another way to think about delta is that it means the finish point minus the starting point. So what do you think delta x means? Correct. Delta x stands for the change in position. The change in position is a definition of displacement. So that means displacement equals delta x. Mathematically, this can be written as the finished position represented as x sub 2 minus the starting position represented as x sub 1. Below is an example of a positive displacement. According to the equation, x sub 2 minus x sub 1, the displacement equals 20 meters. The next example shows a woman running, or more like power walking, in the negative direction. This time, when you use the displacement equation, you get a negative 20 meters. An important concept to remember here is that the direction of the displacement is represented by either the positive or negative sign in front of your answer. Let's do exercise A. An ant starts at 20 centimeters on a graph paper and walks along the x-axis to a position of negative 20 centimeters. It then turns around and walks back to a position of negative 10 centimeters. We want to determine A, the ant's displacement, and B, the total distance traveled. The first step for part A is to write the equation for displacement. Delta x equals the final position minus the initial position. So we have negative 10 as the final position and positive 20 as the initial position. This equals negative 30 centimeters. To figure out the total distance, we need to break it up into two parts, taking the difference of the first segment and adding it to the difference of the second segment. Notice that we take the absolute value for distance, and that while taking the difference between both segments, notice that the two negatives equals a positive. So the first segment is 40 centimeters, and the second segment is negative 10 centimeters. Applying the absolute value sign, we get 40 plus 10, which equals a total distance of 50 centimeters. Notice that the negative sign matters with displacement because it's a vector. The negative sign tells you that the arrowhead is pointing in the negative direction with a magnitude of 30. Whereas distance, there is no one direction, just only magnitude of a total distance of 50 centimeters. A formal definition of speed is how far an object travels in a given time interval. What you need to understand is that the average speed equals distance over time, which is represented by the variables below. The bar over S indicates that the speed is an average. In the example below, we already learned that the distance traveled is 70 meters. Let's pretend that this graph represents a football player running a play. And let's say it takes the football player 10 seconds to travel 70 meters. How would you solve for the average speed of the football player? That's right. You divide 70 meters over 10 seconds. Thus, the average speed of the football player is 7 meters per second. The difference between speed and velocity is that velocity includes direction. So mathematically, the average velocity equals the displacement over time because displacement also depends on direction, whereas distance does not. If we again pretend that a football player is running a total distance of 70 meters in 10 seconds, what would the average velocity be according to the graph below? Great job! You would take the final position of 40 meters and subtract it from the starting position of 0 meters and divide the whole equation by 10 seconds to obtain an average velocity of 4 meters per second. Please take note that the time is still 10 seconds for solving the average velocity, even though the football player took 10 seconds to actually travel a distance of 70 meters. Let's do example 2.1. The position of a runner is plotted as moving along the x-axis of a coordinate system. During a 3-second time interval, the runner's position changes from x1 equals 50 meters to x2 equals 30.5 meters, as shown above. What is the runner's average velocity? First step, write out the definition of velocity. Change in position over change in time, or the final position minus the initial position over the final time minus the initial time, which usually always equals 0. Now it's time to plug and chug with the variables given. You have 3.5 meters minus 50 meters all over 3 seconds minus 0 seconds, which equals negative 19.5 meters over 3 seconds, thus giving you negative 6.5 meters per second. So the runner is moving in the negative x direction with a magnitude of 6.5 meters per second. Alright, here's example 2.2. How far can a cyclist travel in 2.5 hours along a straight road if her average velocity is 18 kilometers per hour? Again, the first step is to write out the definition of velocity, change in position over change in time. But we're actually solving for how far, which is displacement. So we need to rearrange the equation to solve for delta x. Now we can plug and chug. (18 kilometers per hour times 2.5 hours). Notice that the hours cancel out. And now we're just left with kilometers, which is a good sign because we're solving for how far, or displacement, which equals 45 kilometers. So the cyclist traveled 45 kilometers in 2.5 hours with an average velocity of 18 kilometers per hour along the straight road. Alright, last example. A car travels at a constant 50 kilometers per hour for 100 kilometers. It then speeds up to 100 kilometers per hour and has driven another 100 kilometers. What is the car's average speed for the 200 kilometers trip? The first step, again, is to write the definition of average velocity, change in position over change in time. We know the displacement is, or the change in position for the car's trip to be 200 kilometers. However, what we don't know is the total time it took the car to travel 200 kilometers. To solve for the total time, we need to take the information given to us earlier about the trip and solve for time. We can rearrange for time with using this equation so that we have change in position over average velocity. Since we have two segments, we can write this as change in position over the average velocity for the first segment and also for the second segment. Then we can plug and chug. Notice that the kilometers cancel out, and we're only left with hour for time. The total time for the first and second segment is 2 hours for this first segment and 1 hour for the second segment, which gives us a total time of 3 hours for the whole trip. Now we can solve for the average speed. Plug and chug, and we get 66.67 kilometers per hour as the average speed for the entire trip. Now keep in mind, the incorrect way to solve for the average speed is taking the average speed between the two segments, that which would give you 75 kilometers per hour. This is incorrect because the car spends more time in the first segment of 100 kilometers at a slower speed than the second segment, so the car's average speed should be less than 75 kilometers per hour.